Hello and welcome to today's SEI webcast. Can you rely on your AI? Applying the AIR tool to improve classifier performance. My name is Shane McGraw, Outreach Team Lead here at the Software Engineering Institute, and I'd like to thank you for attending. We want to make today's webcast as interactive as possible. We will address questions throughout today's talk, and again at the end. You can submit those questions in the YouTube chat area now. And as I mentioned, we will get to as many as we can. Now I'd like to introduce our panel of SEI speakers. Linda Parker Gates is the principal investigator for the long-term research project on AI robustness, and she will serve as our moderator for today's panel. Crisanne Nolan is an agile transformation engineer in the Continuous Delivery of Capability Directorate. Mike Konrad is a principal researcher in our Software Engineering, Measurement, and Analysis Directorate. Nick Testa is a senior researcher specializing in AI and ML and causal inference. Suze Miller is a principal researcher working in the Continuous Deployment of Capabilities Directorate. And lastly, David Shepard is a software developer within our Software Solutions division. Now I'd like to turn it over to Linda Parker Gates. Linda, good afternoon. All yours.
Hi, Shane. Thank you very much. Yes, I'm Linda Parker Gates, and I am the principal investigator on an exciting research project that we're doing at the SEI. Our researchers have done some really novel and very promising work in causal discovery and causal inference that kind of allows us to go past or beyond typical analytic methods and do so with unprecedented confidence. So we're going to tell you today about a tool called AIR that embodies the math that will be described to you in this webinar. And then our goal is to try to find some partners who will share AI/ML data sets with us and allow us to apply the method and validate its effectiveness in various applications and contexts. So I've got a big crew with me here today to talk about this project, and it includes people who have kind of been part of imagining this solution from the beginning and others who have helped bring it along. And we're going to talk to you about the tool and again, invite you to think about whether you'd like to be a partner with us in this research. So first, I want to introduce Mike Konrad and Nick Testa. Again, reintroduce, I should say. But Mike is I'm going to say, Mike, that you are a brilliant mathematician. And you've been working on this solution since its inception, really bringing causal inference and causal discovery together in what I think is an impactful way. And then Nick is a fantastic newer addition to our team, really bringing, among other things, a real ability to explain complicated and nuanced things. So no pressure, Nick.
Yes, thanks.
So let me start by asking Mike if in a few sentences you can describe the problem that we're trying to solve and how the AIR tool addresses that problem.
Thank you, Linda. So we live in interesting times, and we have artificial intelligence and machine learning solutions being employed increasingly as the underlying technology develops. But somebody along the way hopefully is asking, how do we know it works? And do these solutions do what we expect of them? Can we rely on their predictions? So we invented the AI robustness tool, AIR, or AIR, for the purpose of looking at maybe at a data set deeper than a typical machine learning or AI approach would, in order to uncover causal relationships. And once you have a handle on the causal relationships, you can answer tough questions about what might happen next if we were to do something, some kind of intervention or perturbation. And so that's what the AIR tool calculates. So what happens without AIR? You go ahead and use your AI and ML solutions and sometimes they will let you down. They will let you down for somewhat subtle reasons. There can be what's called confounding. That's where you have a common cause that affects both a variable representing the context or a scenario that you're in, and the outcome of interest, like mission success. And when when the training data for an AI or ML system isn't adequately representing the particular question or mission that you're envisioning, then it will give you a biased answer. The math is very simple and definitive on that.
We've had some, there are some examples of that you read about in the news. Like I read about a recruitment tool, not to name any particular business, but where historical data was used to evaluate resumes, but because the historical data included more male resumes than female resumes, the algorithm sort of started to train itself to favor male applicants, right? So things like that can start to happen. I think there's a good real estate example too of kind of skewing the value of properties and unintentionally buying things above value. So and Mike, so you're starting to talk about data, I think data drift, concept drift, edge cases, things like that. I wondered, Nick, if you wanted to add anything about kind of specifically what kind of robustness we're talking about, and then why that's important, why that kind of AI robustness is important.
Yeah, of course. Thanks, Linda. So there are a couple of different ways we talk about robustness in the kind of AI space. There's kind of robustness to like external factors, which is like adversaries and hackers and stuff. And then there's robustness to more internal factors like the model and data drift. And that's kind of more what we're focused on here. And to clarify, what we mean when we say robustness is kind of the ability of the model to produce accurate results across a range of different use cases or scenarios. And so here we're really trying to make sure that we don't have any issues when we use the AI classifier across, edge cases, or when we run into corner cases and stuff. We want to make sure that it's functioning exactly as it's intended to.
Do you, Nick or Mike, have an example you can share about what happens when, what can go wrong when classifiers are not robust?
I'll
You want to take this,
provide
Mike?
an example.
Okay.
Yeah, thanks, Mike. Go ahead.
Yeah, thanks.
Actually, in the example that Nick's going to show us, we may have been taking off for some period of time at a high altitude where it's cold all the time. And we may observe that when we make certain decisions, or whether let's say mission software is making decisions driven in part by an AI or ML solution. When that's the case, and if the AI or ML solution was trained on data only from high altitudes and cold, then it doesn't know there's no basis for the solution, the AI or ML, to learn how the mission might unfold or what might happen, because it's simply not in the data. But it can be more subtle than that. Maybe there is a particular person in charge who is always favors the high altitude cold, but also has a maybe very rigid criterion for success. In which case you might have a situation where unknowingly the missions of this particular high-ranking individual might have a higher failure rate. Right. And if you just looked at the correlation, you might not see that. It might be lost in the noise. So that's what the causal system is intended to unearth.
That's a great example. Thanks. So actually, you mentioned a little demo that I'm going to ask Nick to do for us now. And along the way, if you can kind of explain what's happening along the way. I think that would be real interesting. So Nick?
Yeah, of course. Okay, so here, so what's my screen is shared here. So I'm going to take us through a demo of kind of a fictitious entity that's hoping to build an AI classifier to predict mission success of let's say in this case, like a UAV drone, based on mission parameters and base location. So what we're trying to do is predict this mission success. And here we're defining this as the drone successfully acquiring images of its target. In this little example here, maybe it's a little stretch of road or something. Our client knows that many of the mission parameters, things like maybe mission urgency or region sensitivity, could affect both which base is chosen and also aspects of mission success itself. Additionally, other variables like the environment at the base, things like humidity, temperature, altitude can also affect success in other unrelated ways as well. So we want to be able to understand not just what mission success looks like based on which main base is used, like whether or not the drone is taking off in the mountains, in the cold mountains, or in the hot desert, in this toy example here, but also kind of why and what factors are contributing to that success. Unrelated events, could potentially end up changing the environmental variables enough so that the classifier performance starts to degrade. And we want to make sure that we're aware of that and staying one step ahead of it and understanding what's going on. To do this, normally we have to invoke tools like causal inference. Unfortunately, we need to have kind of a full causal graph to make that work. We need to understand really well the cause and effect structure, like chain of events that goes on here. And that's not something we always just have on hand.
Yeah, that's what I was going to ask, Nick. Yeah, do people have those on hand? What happens when they don't?
Oh, yeah. So normally, no, they don't. We can get a pretty good idea usually, kind of rough causal effects. But yeah, normally this isn't something that we're going to have. And so this is one of the biggest arguments, or this is one of the things that you need to be able to do this kind of analysis. So fortunately, that's where the AIR tool really shines. And this helps us build out a likely causal graph that we can then later use for causal inference. So the way it works is at first we would have kind of subject matter experts, in this case, people that run, the UAV drones, work with our analysts to define a rough hierarchy of kind of cause and effect relationships within the data. This is the kind of thing that we would already kind of know, but it's important that we have it formalized and written down. So each of these layers is assumed to be able to influence all the members of its own group and everyone downstream, but not upstream. And this is important because, for example, we might expect something like ambient temperature to influence ice accumulation on the drones, but not the other way around. I mean, that seems obvious, but it needs to be explicitly stated. Then the SEI analysts will generate the most likely causal graph using hierarchical relationships in combination that we just mentioned with the raw data used to build the original classifier. And that gives us this causal graph we see here with main base being the variable of interest that we're looking at varying and the images acquired being mission success. Unfortunately, though, we can't take this graph straight into the causal inference trap just yet. One of the issues we need to deal with is bias. Anytime we see variables with common causes, things like mission urgency, or multiple causes, those like the intermediates have multiple causes. We know those can introduce bias into the results, and we need to control for that. So causal identification is the next step of the AIR tool, or the AIR approach, that allows us to tease apart some of those confounding issues. This next step breaks the causal diagram into two main groups that we call conditioning sets. The first group on top in black takes the original graph and breaks the causal connections of common causes associated with main base and images acquired. And that leaves us with one part of the causal graph. The second group with the gray arrows breaks up the causal effects of the upstream mission variables on the intermediate environmental variables. And this might seem kind of like a subtle and arbitrary difference, but it's crucial to understanding how big an effect main base really makes on images acquired, on mission success. So once we have these two conditioning sets, we can then use them as inputs for our causal inference step. Okay, so we're finally here at the causal inference step. Remember, the goal here is to use cause-effect relationships to answer the question, what if? Well, here we make use of both conditioning sets, the black and the gray, to apply a kind of and then we apply a kind of ensemble of doubly robust estimators to produce an answer to our specific question. What if we did the same mission, but just changed which base we started from? What effect would that have on mission success in general? So the result we get here is both a point estimate, you can see the little dots, as well as a confidence range. And that's the bars that extend up and down from the dots. Ranges like this basically correspond to the upper and lower limits of how big of an effect we expect main base to have on mission success, images acquired. So if everything looks good and those ranges aren't too dissimilar, we can then compare with the average treatment effects predicted using AI classifiers. So in this fictitious example, how did our client's AI classifier stack up against our approach, you might ask? Well, here we can see the AI classifiers in red, or pink, I suppose, have a treatment effect outside the bounds of our causal inference-based estimations. Looks like their models are predicting pretty much no difference in mission success when the drone takes off from another base, while our causal-based estimator predicts a pretty strong range of effects comparatively. So this tells us these AI classifiers are probably missing something, and we need to go in and investigate. Eventually, the AIR tool is going to incorporate kind of a more full and comprehensive health report of your classifier with recommendations based on these results and the full causal graph, but it's still a work in progress.
So, so not only are you getting better predictions and things that are less biased, but you are working now with information that's sort of more suitable for intervention or decision-making or control.
Oh,
is that right?
Absolutely. Yeah, it's less of a black box now, right? Mm-hmm. So we have a more explainable kind of roadmap that we can use to assess the health of the AI classifier.
Yeah, so if you're doing something mission critical, that attribution of outliers and the ability to see inside that black box, as you said, and make decisions is pretty important. But so let me ask you, Nick, what kinds of how broadly can this solution be applied? What kinds of things can AIR be applied to, other than what, you know, the kind of thing you talked about in this example? Can you speak to that a little bit?
Yeah, so of course. So anytime we have AI classifiers where we are trying to vary, we are looking at the effect of one like particular treatment variable on the success or classification of another variable. This is where this really shines. I think Mike might be able to talk a little bit more specifically about how generalizable this is. Mike, do you have anything you want to add?
Just that it's very broadly applicable. It can apply to any black box function. You don't need to know the internals, hence the black box, but it's just something that takes input and produces predictions or output. It can be AI based. It can be a polynomial equation. It's really quite general.
Yeah, and I think as long as we have a sizable enough environmental data, as long as we have enough data to work with, right?
And the variety of data is particularly important. You want to have potential causes, and subject matter experts can help with this, but they can. And hopefully anybody who's been using operational data for a while will have given some thought about what kinds of data Do we need to gain insight into mission success? And those are exactly the kinds of variables that the AIR tool uses.
Thank you. Yeah, and I wanted to highlight that because, as I mentioned, we are looking for partners. We want to work with a variety of types of programs, even a range of organizations to see what it looks like to put this tool into practice. And so we want to do that in as many places as we can and learn about not only how the tool works, but what's involved in adoption. So I kind of want to pivot now to introduce Suze Miller and Crisanne Nolan, who are world-class researchers and practitioners in technology adoption. They are on the team to help us install and trial use and all those kind of buzzwords around tech adoption. And Susie's going to tell you all the details about that. So can you talk about what it means, Suze, to adopt a new technology and kind of describe how we would support programs who are interested in partnering with us?
Of course. So some of you may know the SEI has done research in technology adoption for decades, literally. Most of our active research was in the early 2000s, but ever since then, we've been applying what we learned in that research to lots of different settings, program settings, and lots of different technology settings. And so we do have kind of a standard process for helping organizations to adopt a particular technology. And we have a set of things that we're particularly interested in when it comes to this particular technology, which is we're calling AIR. And that is really related to the fact that we're trying to make sure that we understand what does it take to actually adopt this stuff. I mean, if I'm not a mathematician, and if I talk to Mike for very long about some of the mathematical aspects of this, I'm not going to get very far. But I also know that there have been settings that I've been in where having some way of understanding what's happening in our system and why it's doing the things that we do, whether it's polynomial based or AI based, as Mike said, is very valuable. And so we want these kinds of tools to become available to the DoD community, to the larger community, in ways that are adoptable by the Susie Millers of the world, as well as the Mike Konrads and the Nick Testas and the kinds of decision makers that have to do things related to adopting this kind of way of thinking about our AI ML systems. And
which is increasingly more and more people, right, Suze?
Yeah, and so partners initially are going to help us with understanding what some of the particular barriers are for the state of where the AI robustness approach is right now. Over time, we want to be able to actually make more generalizable kinds of what we call adoption support mechanisms available to the larger populations that may be adopting this kind of approach. So we have a lot of things planned once we have somebody to actually work with that allows us to help them to make a successful adoption of AIR and make it useful for their population.
So how do you know what kind of adopters or adoption support, I'm sorry, different groups will need?
All right, I'm so glad you asked that. And so I've put up a slide. I've got a slide up here called the Adopter Continuum, which I think will be able to show. Am I showing that? Yes, there it is. And so any of you that have done any work in technical marketing, technology adoption will recognize this. This is a graph that shows the categories of adopters that we generally talk about when we talk about who is going to be adopting a particular technology. And it's based on the population's reaction to that technology. So innovators are a group that tends to take the new thing, AIR, and really be more interested in it itself and why it works than they might be in the actual results of it. They have a lot of interest in the why does it work kind of thing. Early adopters tend to be what we call visionaries because they're really interested in what can I do with this? How can I make my mission more successful or my business more successful? And they'll tolerate some newness and some sort of bumps in the road in terms of adoption support to be able to get the result they want. The early majority group is much more pragmatic. We call them the pragmatist. And they're willing to do something that has a visible ROI. They're willing to accept some level of bumpiness, but they really would not like too much bumpiness in terms of their adoption path. Late majority tend to be our conservatives. We also call that sort of the Main Street group, where there's an expectation that if you bring me a new technology, it's going to be wrapped up in a bow, and it's kind of going to be a single push button for me to get my results. It's not going to make me change the way I think about things or do things very much. Laggards are the skeptics, the folks that say, I'll retire before I do this. Are the people that are really looking at all the risks of any technology and don't really want to have anything to do with the new technology. When we start talking about adoption support for a technology like AIR that is still relatively new in terms of its stages of maturity, we're really looking at the early adopters and early majority groups as our primary groups that are of interest for us to partner with. And you'll notice there's a large gap between the early adopters and the early majority called the chasm. This is Jeffrey Moore's coining of that term. And that really indicates that these two groups do have different ways of communicating and have very different needs for adoption support. And so one of the adoption research aspects of this work is, can we get some people on both sides of that chasm and understand better what are the things we need to do to support early adopters versus what are the things we need to do to support the early majority. And so those are important. That's an important aspect for us. So when you're thinking about whether or not you may want to work with us, you can probably put yourself in one of these groups. And we have other ways. We're going to talk about some more specific things. Crisanne is in just a minute, that we're sort of identifying what are some of the user classes that we think are going to be involved in working with this technology, and how we can sort of tune our adoption support mechanisms to those different groups. So at this point, I actually am going to turn it over to Crisanne to talk about what are the kinds of roles that we would expect to be using something like AIR, and what sorts of things those people might be doing that would lead you to think that, oh, that could be me. This could be something that we actually would want to do something with this. Go ahead,
Right.
Crisanne.
So please listen for yourselves as Crisanne's describing these roles.
Hi, thank you guys. Yes, I would like to share a little bit about the work our team has been doing about user classes. So in preparation for engaging a partner, we've spent time thinking about the kinds of roles that people will have when they use AIR. We're not really thinking so much about job titles, more about what kinds of work goals would someone need to accomplish. For a partner, it might be a whole team has this kind of a user class. It might be an individual person in that user class. Or for a small group, it might be one subject matter expert that wears 3 hats. So we're up for that kind of flexibility, but we're thinking really in that kind of a user class role, what kinds of goals do they have and what kind of work will they need to do successfully with the AIR? So an example would be machine learning engineers. They'll be key to this method. They'll help identify test cases for AIR and lead sort of the collaboration to validate the usefulness of the data. They'll be working with a user class like data engineers, the people who will be engineering the data products that will drive the causal discovery and causal inference. We also plan to support like quality engineers as a role, as a user class. So that would be the kinds of people who are making sure that AIR is using appropriate V&V methods and is analyzing anomalies in the results. Sort of the NICS demo, you got an idea of what kinds of results you might see. We'll need to engage with someone in a user class to make sense of that and put it to use. And of course, we want to support program leaders, the people for whom adoption means using these results from the machine learning and making really tough decisions. So letting them be able to interpret and understand and explain the information coming to them that they haven't seen before. We expect that people in all of these user classes are likely to be part of the testing community, and that's generally still kind of warming up to the idea of using AI classifiers. So our user class planning also includes thinking about how we can help partners to see barriers and work on mindset changes that help put AIR to use. That is different ways of thinking. So it might be thinking about testing AI classifiers differently than thinking about testing traditional software, or changing a mindset to use causal inference as a new method to build confidence in results. Our plan going in is really to think about an adoption strategy for a particular partner that lets us kind of choose and customize the sort of adoption mechanisms that Suze mentioned earlier, things like training and coaching and support materials, to address both the skills and procedures for deploying the tool to these user classes, as well as working with them on the mindset shifts to make robust AI really work for them and be durable into the future. Back to you, Suze.
Thanks, Crisanne. So Crisanne mentioned the idea of adoption support mechanisms, and that's really the piece that is the partnering that we really need to do with people that are using AIR, is to figure out what kinds of elements like training and what kinds of governance needs to change, what kinds of processes need to be adopted. Talked about testing and some sort of testing mind shifts that may lead to some different processes. So all of these things are adoption support mechanisms that we want to be able to tune to particular settings. So the setting that Nick gave us as sort of a UAV, kind of mission success prediction kind of setting might have a very different set of characteristics than an organization that's using AI classifiers to analyze different kinds of errors that are coming out of different procedures that are being conducted on jet engines or other kinds of mechanics. And so we know that in different settings, we're going to have to do different things. But what we don't know is how different do they have to be? Are there generalizable things that we can do? Are there some, I can pretty much predict that not everybody in the world understands causal inference and causal discovery the way Nick and Mike do, right? So we're probably going to have to do some things around that. We're also going to need to do some things to figure out where are the right places for automation. Where can we automate some of these processes that Nick was talking about in terms of going through causal discovery, getting to causal inference, making the causal relationships visible? Some of those are going to be more amenable to automation than others. And we also know that if I look across, no technology environment from one setting to another is the same. So to what extent do we need to provide people with understanding of basic technology prerequisites where there are some, or how flexible can we be in terms of being able to provide automation kinds of things? We have Dave Shepard as one of our automation experts who is looking right now at sort of how do we use this in a web environment, which seems to be the sort of baseline, that's the simplest environment that almost anybody can get to. What can we do in that environment that allows the most users to be able to do something? But on the other hand, as soon as we get into situations, which we know about also, where you have data that is sensitive, data that is classified, we're going to have to adapt to those kinds of technical environments as well. So we're trying to understand all of those things. That's really the transition research part of this, is understanding for this, what we think is a very impactful way of understanding the reliability, the robustness of our AI classifiers. What do we need to do to make that accessible to the largest number of people that really need that kind of information? And so that's really what the transition part of this research is about.
Thanks, Suze. So let me ask Shane, do we have any questions coming in at this point?
No current questions, Linda, but there is a poll that was added to the YouTube chat, just asking for people their interest in the tool. People can take a look at the chat area and get back to us there. But yeah, no audience questions yet.
Okay, so then let's see. Was there? I know that I want to end with a broad invitation to people. If you have AI classifiers, if you're using AI classifiers, if you are particularly in that early or early adopter, early majority category that Suze described, we are very interested in talking with you. This is sponsored research, so it is fully funded, and we're really looking for people who can share their context, their data sets with us, essentially, because we don't really learn unless we have real data to work with, and we don't really learn about the impact unless we're able to show sort of some measured benefits. So if you are interested in collaborating with us, please let us know. Shane will let you know kind of how to contact us. And let me just ask if anyone has any closing thoughts from the panel. Yeah, Mike.
Great. Just a couple of quick points. Nick showed one scenario, which base you took off from. We have applied this tool with 10 scenarios at a time. So you can imagine 10 of those graphs, each one with 2 confidence intervals and the results average for several classifiers.
Yeah, that's a good point, Mike. It's not limited to just one treatment.
Yeah. Okay.
Yeah, and I just want to say quickly, this is a great team to be part of, just from my perspective. This is some of these folks I've known for many years, and it's a delight to be working with them. So I just want to get that out. I'm sorry.
I agree with you, Mike. Join us, come work with us. If no one else has any additional points that they wish to make, I will hand it back to you, Shane.
Panelists, great discussion today. We really thank you guys for sharing your expertise. Wanted to remind everybody, upon exiting today, please hit the like button below and share the archive if you found value. The archive will be the same URL that you're viewing today. Also, you can subscribe to our YouTube channel by clicking on the SEI seal in the lower right corner of the video window. Our next webcast will be June 12th. The topic will be Secure Systems Don't Happen by Accident by Tim Chick. Registration information is available on our website now and will be emailed out as well. Any questions from today's event, please send to info@sei.cmu.edu. Thanks, everyone. Have a great day.